Right, so today is again Wednesday, and today we are going to talk about pressure vessels. Very different topic than what we've been discussing for a while now. We've been talking about beams. Before we get started, though, I wanted to mention that I did finish grading your test. I had intended or planned and hoped to get those grades entered in Canvas this morning, but something else came up, so I did not have time to do that this morning before class. But I can tell you, sometime early this afternoon after class, I will get your test grades put in the gradebook in Canvas, as well as post the solution to test 3 also in Canvas. Just FYI, in case you're curious or interested, overall, the grades on the test were pretty much like the last test. If you're interested or curious, the average, I wrote it down here, 77.4 was the average. So it was 78 point something on the previous test. So pretty close. Again, some did a little better, some did a little worse, some did about the same. Overall, about the same as the last test. Although I think on the last test nobody made 100, but there was 100 on this test. So one lucky person made 100. There were several other 90s, but I'll get those grades posted in Canvas sometime early afternoon. So you can check back later, see what you made, pull up, look at the solution. All right, but so back to what we're going to talk about today. Couple of things. One, first off, make sure everybody's clear. When we say pressure vessel here, we're talking about a positive internal pressure. We're not talking about any vacuum chambers. So the pressure inside is always going to be greater than the pressure outside. Right? We're not, again, we're not pulling a vacuum here. That is a completely different animal to try to analyze. Formulas we're going to come up with here in just a few minutes, totally irrelevant to if you got a negative pressure and you start pulling a vacuum. Other thing, the formulas that we're going to come up with in just a minute only apply to what we refer to as thin-walled pressure vessels. So these are the pressure vessels where the thickness is much, much less than the size, the radius of the pressure vessel. In fact, I think this particular textbook uses ratio R over T. It's got to be greater than or equal to 10. So we'll see in a minute, R here is the inner radius of this pressure vessel. It's got to be at least 10 times the thickness for these formulas to apply. And in fact, I think there's discussion in the book. I think the whole purpose in limiting ourselves to thin walls is that if the wall is really thin compared to the size of the pressure vessel, the stress doesn't change much from the inner surface, the inner wall, to the outer wall. If you start getting really thick wall, then there is a significant difference between the stress on the inner wall and the outer wall. And those types of pressure vessels are analyzed differently than what the formulas that we're going to come up with and use. But most pressure vessels are thin-walled, would meet this criteria, because we'll see in order to keep the stresses below our allowable, the thickness doesn't have to be that great. Really thin wall can withstand a great deal of pressure. And these are very common types of structures. You see pressure vessels all over the place. You see, like, if you got a gas grill with a liquid propane bottle, that's a pressure vessel. If your house has gas, you got a big gas storage tank at your house, that's a pressure vessel. If you say live in town and just have gas lines, well, turns out all any kind of piping is just a long cylindrical pressure vessel. So piping and cylindrical pressure vessels essentially the same. So just think about all the places you have not only what you might first think of as a pressure vessel, but any kind of piping. The water pipes come into your house, cylindrical pressure vessel. So these things occur all over the place, and we're going to look at two types, a cylindrical vessel and a spherical vessel. By far and away, the two most common types, partly because they're the two easiest to analyze. You're going to see we're going to come up with some really nice, short, easy formulas that we can use to calculate the stress in these pressure vessels. All right, so I mentioned we're going to look at two. The first one we're going to talk about is cylindrical. So as the name implies, it's a pressure vessel that's shaped like a cylinder. Now, we're going to see with all these pressure vessels, these things are subjected to what we call biaxial stress. So that implies there's stress in two directions, right? We're going to have stress in two axes. And so if you look at if you looked at a little element, a little piece of the side of this pressure vessel, you're going to see a stress in the axial direction. We'll denote sigma A. All right, this is the axial, or the stress in the longitudinal direction. Right, if you got a cylindrical vessel like this and you put pressure in it, then that pressure is trying to pull this thing apart this direction, right? You got pressure pushing to the left, you got pressure pushing to the right. It's trying to basically pull this thing apart longitudinally. And the stress is in that direction, we're going to call the axial stress. Right? But if you have pressure in here, it's also trying to, I don't know the best way to do this, but maybe I get two hands. It's trying to basically blow it apart in this case, the way my picture's drawn, in the vertical direction. Right? You got pressure in here. It's trying to basically push that top up and push the bottom down. And that stress in what would be referred to as the circumferential direction, which is very long and hard to say and hard to write. So this is typically referred to as the hoop stress. But if you prefer, you can call it the circumferential. If I could spell circumferential stress. Right, so when you put a pressure inside this cylinder, again, it's trying to basically blow this thing apart in two directions. And these two stresses, that's what we're going to try to come up with a formula that will allow us to calculate those stresses in the longitudinal direction and the circumferential direction. Now, here's where the thin wall part of this comes into play. Right? If you look at the cross section of this cylinder, right? We're going to have the inner radius we're going to denote with R. The wall is going to have some thickness, T, and this would be the area of the wall. Now, to get the actual area of that wall, again, what you could do is take the area based on the outer radius and then subtract the area based on the inner radius, and the difference would be the area of that wall. But here's where, if the thickness T is really small compared to R, then we can approximate. Okay, so if we've got a thickness that's much, much smaller than radius, the area of the wall is going to be approximately equal to the circumference of the inner circle times the thickness, or just 2 pi r t. And this formula we're going to come up with is based on this assumption. We're going to use this approximation. That's why the formulas we get start to break down as the thickness gets bigger, right? Now, remember when we talked about normal stress, right, we said normal stress was, I'm going to use F instead of P over A, just because P here we're going to start using for pressure. But we could get the force by multiplying the stress times the area. Right? We've done that a couple of times when we were deriving some other stuff. So if you've got a stress acting over a surface area, then the equivalent force associated with that stress is just the stress times the area that it acts on. So it's exactly what we're gonna do here. We're going to cut this cylinder. Right? If we cut it in this direction, and if I can drawing circles are hard, especially when they're hard for me. All right, so I'm cutting this, and I'm looking at the right side of where I cut it. All right, so we've got this. This is the area of the wall. Right, so this is the area of the wall. Right, and that's where we're going to have this axial stress. We're going to have this. Maybe all these different colors. Yeah, we're going to have this normal stress. That's sigma A acting on that area. So the force that's associated with that, I'll call force sigma, force due to stress, would just be whatever that axial stress is times the area of that wall. Right? That's the force associated with that stress. All right, well, now back here on this back end, and here's where I'm going to defy, I don't know, I don't know what the best term for it. You know, if you got a cylinder, I can rotate it, this way so you can see this end. And if that's the case, then you couldn't see the bottom surface. Or I could rotate the other direction and you could see this surface, but not that one. That's what happens in reality. But I want you to be able to see both surfaces. So I'm just telling you this because I know somebody's sitting out there thinking, well, there's no way we could actually be seeing both ends of this thing. I'm agreeing. I'm telling you that, but I'm drawing it so that we can actually see both ends for visualization purposes. All right. So on this end, right, what we've got is we've got this pressure. All right, we've got this internal pressure pushing on this thing, and so we're going to get and that pressure is pushing on this area. Right, remember this thing's got radius r. All right. Well, the force that's associated with that pressure, again, you learn this in physics when you study pressure, right? You got a pressure acting on a surface. The force is just the pressure times the area. It would be the pressure times that area that the pressure is pushing on. Well, we know if this is in equilibrium, forces have to add up to zero. And so if this is in equilibrium, sum of the forces equals zero, then I know the force due to the stress has got to equal the force due to the pressure. So I just set those two equal, and we solve for stress. So this is going to be, again, the normal stress times the area of the wall. This is equal to the pressure times the area the pressure is acting on. Or we're going to use our approximation from up here for the area of the wall, 2 pi RT. And the area that the pressure acts on is just the circular area, which is pi r squared. Pi's cancel. One of the r's cancel. And when you solve for the axial stress, you get PR over 2T. So, not real super complicated derivation of where this formula comes from. Remind you here that P, this is the internal gauge pressure. R is the inner radius. T obviously is the wall thickness. And so that's our first formula. We've got, if we want to know what the axial stress is in a cylindrical pressure vessel, very simple, it's just PR over 2T. So if you know the pressure, the inner radius, the wall thickness, you can calculate that axial stress. All right, any question about this formula? All right, well, we're going to do a similar exercise to come up with the formula for the hoop stress, the stress in the opposite direction. Now, how we're going to do that is we're going to cut it the other direction. So now, picture, if you will, slicing our cylinder lengthwise instead of chopping it in half across the cross section there. We slice it longitudinally. And probably the most challenging part of this is going to be for me to draw this picture. I'll try to draw a 3D picture depicting our cylinder. Ooh, that's not super great circle, but we'll go with it. Ah, well, that's messed up. Yeah, that's as best as you're going to get from me. But that's if we took this cylinder, sliced it lengthwise. Now it's going to have some length L, and this distance across here, this would be 2R. Right? Remember, R is the inner radius. So that distance would be 2r across there. All right, well, just like up here, we had this axial stress acting on the wall. Right here, we're going to have that hoop stress. So that's the normal stress that's acting on that wall, right, which I remember has some thickness, T thickness. Right, so you got this pressure. You got this pressure that's pushing down on this big rectangular surface, right? So you got this. Yeah, I'm not gonna. It's gonna get real cluttered. We'll just go straight. You're gonna have the force that the pressure is pushing down is going to be equal to the pressure times that big rectangular area that the pressure is pushing down on that surface. And then you're going to have the normal stress in the wall, right, you're going to have an equivalent force due to the stress. I don't want to make it too clear. Yeah. In fact, might help or might be a little clearer. I can do much better in 2D. If we just look at a 2D picture at the end of this thing. Again, we've got the force due to the pressure is equal to the pressure times, again, the area that the pressure acts over. And then we're going to have a force due to the hoop stress, right, in each of those two walls. Now, the magnitude of each of those is going to be the same. It's going to be whatever the hoop stress is times the area of the wall here. And I'm going to put a little prime just to distinguish. This is not the same thing as the area of the wall up there. It's a different. So we'd have the hoop stress. So we're going to do exactly the same thing we did before. We're going to set them equal to each other. All right, so again, I know the sum of forces got to be 0. So here, I've got 2 of these forces due to the stress. It's got to be equal to the force due to the pressure. So the force due to the stress is equal to the hoop stress. Now, the area that it acts on is T times L. Right? So this is U times TL. That's what that area of the wall would be equal to, whatever the thickness of the wall is times the length. So plug that in. The force the pressure causes is the pressure times this big rectangular area, which is 2R times L. And again, we can cancel some stuff. The 2's cancel. L cancels. And our hoop stress should come out to be PR over T. So there's our 2 formulas that we're after. Nice, simple, pretty straightforward, easy to use formulas. We can calculate the hoop stress. We can calculate the axial or longitudinal stress. One maybe note here, you might have noticed this, but if you look at these two things, they're very, very similar. In fact, they're almost identical. The difference being the axial stress is PR over 2T, and this is just PR over T. So the hoop stress is twice as large as the axial stress. Hoop stress is twice the axial stress. So this is why the hoop stress is going to govern the design if we're designing this pressure vessel. Governs. So in other words, if you're trying to decide what's the maximum pressure you can put in this vessel, or what the minimum thickness has to be, the hoop stress is going to determine that, because it's twice as large as the axial. If this cylindrical pressure vessel fails, right, if you put too much pressure in there and it bursts, it's going to fail due to the hoop stress. So cylindrical pressure vessel fails due to hoop stress. So if you've got a cylinder and you put too much pressure in there, if it bursts or fails, ruptures, whatever term you like to use there, it's going to be because of the hoop stress. It's going to split open. If you go back to the original picture, it's going to split apart this way. It's not going to split apart longitudinally. It's the same material. So that material is going to fail whenever it reaches its ultimate strength, and it's going to reach it in the circumferential direction way before it reaches that stress in the axial direction. In fact, there's a very good picture in your book. Let's see if I can. I'll try to put this up here, and we'll see how this works. I don't know. I'll move this. That's not too bad. So obviously it's on page 415, and what you're looking at in this picture, you see this. It's a big long pipe, a longitudinal pressure vessel. And obviously, too much pressure got put in there, and you see how this thing split open. Right? It didn't blow apart in the longitudinal direction, it blew apart in the circumferential direction due to the hoop stress exceeding the strength of that material. All right. So again, they're testing our fire alarm system. So if I don't know if the microphone's picking that up or not, but if it is, ignore it. Don't worry, nothing is bad happening. I don't have to evacuate the building. So anyway, so nice picture there illustrating how the cylindrical pressure vessel is going to fail due to the hoop stress. All right. All right. So anything else related to these two formulas in cylindrical vessels? All right, no questions. Then I got to get a new sheet of paper, and we'll talk about a spherical vessel. All right, so spherical. Again, two most common types of pressure vessels you find are cylinders and spheres. And in fact, well, I'll come back to that in a minute. But a spherical vessel also is going to have biaxial stress. But due to symmetry, stress is the same in any direction. Right? And I can't draw a 3D sphere here, so just kind of use your imagination. I can draw a circle, or kind of a circle. But picture in your mind this, it's a big spherical pressure vessel. Right? And again, you just take some arbitrary little piece of that wall, and it's going to be exposed to this biaxial stress, just like the cylinder was. But due to symmetry, it doesn't matter how you cut this sphere, every cross section is the same. And so the two stresses are going to be equal to each other. And how we can get a formula for that is very similar to what we did before. If I cut this sphere, and we're just looking at this, not real circular. Pretend like it's cut a sphere in half and we're looking at one half of it. We've got this normal stress that's acting on this wall. We'll call it sigma. Again, this area of the wall is the same as it was first time we cut a cylinder. Right, a wall there we're approximating is 2 pi RT. We've got some inner radius R. Well, we're going to have the force due to the pressure is going to be acting on that area. So that would be the area the pressure acts over. So the force due to the pressure is going to be equal to the pressure times that area. Force due to the stress is going to be equal to the stress times the area of the wall. Like we did before, it's in equilibrium. Sum of the forces equals 0. The force due to stress has got to equal the force due to the pressure. This would be the stress times the area of the wall. This would be the pressure times the area the pressure acts over. The area of the wall is 2 pi RT. The area the pressure acts over is just the area of that circle, which is pi r squared. Pi's cancel, well, the r's cancel, and what we wind up with for a sphere is PR over 2T. Same as it was for the axial direction of the cylinder. All right, any questions about this formula, how we get the normal stress in the wall of a spherical pressure vessel? All right, so now we got our formulas. You're going to like the problems, I think, in this section. Most of these problems are pretty short and easy. It's just basically using these 3 formulas that we just came up with. What will vary from problem to problem is what's given and what's missing. But it's mainly just applying those simple formulas. Just point out one thing. I mentioned these cylindrical and spherical are the 2 most common. Actually, a very common example. You see these a lot with like these big propane storage tanks. You can actually make a storage or pressure vessel, by taking a cylindrical part, and then people will usually weld onto hemispherical end caps. Right, so you got a cylindrical part, and you got a spherical part. And so you can get the maximum stress in the cylindrical section by using those first two formulas we came up with. Right? So here you're going to have axial and the hoop stress that we did. Here in the cylindrical part, right, you're going to have the stress from that. And you see very common type of pressure vessel is you take a cylinder and two hemispheres and put them together, and you make a pressure vessel that looks like that. All right. Any just general questions about pressure vessels or these formulas before we solve a couple of problems? All right. So let's do one. This one, first one we look at, it's a cylindrical pressure vessel. We're given the thickness is 20 millimeters. The inner radius is 225 millimeters. And the allowable stress, 60, these are megapascals. And we want to find the maximum allowable pressure. All right, so we've got a cylindrical pressure vessel. We're given what the wall thickness is, 20 millimeters. The inner radius is 225. Just to kind of just point out, it said initially we were looking at thin wall vessels where that ratio of R over T was at least 10. Well, this is not much over 10, but the radius is a little more than 10 times the thickness. So this definitely would classify as a thin wall. And whatever the material it's made out of, this is our allowable stress. We cannot exceed that stress in that, whatever the material that the wall is made out of. So what's the maximum pressure we can put in there? Well, first thing, again, we're talking about a cylinder, right? So for a cylinder, remember that the hoop stress is twice the axial. So hoop stress is what determines our maximum pressure. Oh gosh, it's wanting to. My computer was wanting to update, so it was wanting to restart. We don't want that to happen right this minute. All right, so our hoop stress is what's going to determine our maximum pressure. Well, I know that the hoop stress is PR over T. So that's what we're going to use to determine our maximum pressure. So we're going to set the hoop stress equal to our allowable. This pressure will be our maximum. The radius, this is the inner radius, is 225 millimeters. Now, you might be thinking, okay, do we need to convert this to... Michael, you can't hear me? Never mind, okay. Oh, the question was, do we need to convert this to meters? Well, Not necessarily. As long as the radius and the thickness are the same, it really doesn't matter. But it might not be a bad habit. If we want to convert into meters, that's fine. It'd be 0.225 meters. But again, if you do that, then you have to convert the thickness into meters, 0.02. But again, we could have left this as in millimeters, and that's in millimeters. The units cancel there, so it really doesn't matter. As long as they're both in the same. And it's all for Pmax. So I got 5.33 megapascal. Now, obviously, this is in the metric units, and personally, I really don't have any feel for what kind of pressure that is, or what 5.33 megapascals corresponds to in psi. I have no idea. So I don't know if that's really large pressure or not so much low pressure. I don't know. But that's the maximum pressure we could put in this vessel and not exceed our allowable stress. Just to give you an idea, like what some typical values of pressures you'll see, again, in English units. When I worked at NASA, I think I saw lots of pressure vessels. At NASA Marshall, out in the test area, there's lots of pressure vessels out there that store liquid oxygen, liquid nitrogen, hydrogen that they use to conduct. Then we were conducting shuttle engine tests. But some of those pressure vessels, the largest one I can remember off the top of my head, it was a nitrogen vessel that was had stored nitrogen in at 15,000 psi. That's a pretty big pressure. Did a lot of work on some liquid oxygen storage vessels. There's one vessel, it was designed for 5,000 psi, but they wanted to use it at 6,000 psi. And so we had to do some analysis, and they modified a few things, and were able to use it at 6,000 psi. Put that in perspective, like the water pipes that come in your house. I forget. It's either 60 psi maybe, or it's designed for 100. I don't know. It's somewhere in that range, like 50 to 100 psi, or what most typical water lines are designed to. So don't quote me on that. If you're curious, you can probably Google it and find that out. But much lower pressure for water lines compared to some other vessels. Anyway, that was an example with the cylinder. Any questions about that one? All right, well, let's do one more. Let's do a sphere. Here we got a spherical tank. I can't spell. SPH. Here we're given the inner diameter is 69 inches. The outer diameter is 72 inches. Our pressure is 1,500 psi. And we want, in this case, find normal stress in the tank wall. All right, so up there in the previous example, we were given the allowable stress and we're trying to find what the maximum pressure was. Here, we're given the pressure and dimensions of the tank, and we're trying to find what that actually calculate what the stress is in the tank wall. Now, again, for a sphere, it's PR over 2T. And this R is the inner radius. So R is the inner radius. That would be the inner diameter divided by 2. So 69 divided by 2 is 34 and a half. Right, pressure's given. That's the R we're going to plug in here. So the only other thing we need is the thickness. Now be careful here. It might be tempting to say, well, the thickness is going to be 3 inches. Take the outer diameter minus the inner diameter, and that would be the wall thickness. Actually, the wall thickness would be half of that. Right? If you, maybe a picture here helps. Pretend like that's a circle. Right, the outer diameter, that's 72 inches. Right, the inner diameter is 69 inches. Right, but this is the thickness. So that thickness would actually be 72 minus 69 divided by 2. So it's 1.5 inches. That's our wall thickness. And so now we just plug in the formula. So we got the pressure, 1500 psi. Again, we want these dimensions to be the same. They're in inches already, so we're good there. 34.5 inches over 2 times 1.5 inches. And I got 17,250 psi. So that would be the stress in the wall of this spherical tank. And so then we would, depending on what the material is, we'd go check and make sure that that doesn't exceed, the yield stress, and definitely hope it doesn't exceed the ultimate stress. Or if it does, this thing's going to burst open and fail. But that's the stress in that wall, that spherical tank. All right, any question about that? All right, well, we only got a few minutes left, so really not time to start something new. I mean, this is basically not a whole lot else we can do with the vessels. So maybe I'll do one little other thing with this one. We'll add this extra here. Say tank is made of A36 steel. Plain old common structural steel. It's got a yield stress of 36 KSI. That's the yield strength on A36 steel. So what would the factor of safety on yield be for this vessel? Well, to get the factor of safety, we just take what the yield stress is, divide by what the actual stress is. So this in PSI is in KSI, so we need to convert both to KSI or both to PSI. We'll just go KSI, I reckon. So this would be 17.25. And we got a factor of safety of a little over 2.09. And I'll point out there's several sort of national standards. There's ASME, so I know all you mechanical engineers know what ASME stands for, American Society of Mechanical Engineers. That's a pressure vessel code, big 3-ring binder full of stuff about pressure vessels. There's also another, it's a piping code called ANSI, the American National Standards Institute for piping. And both of those require a factor of safety of 2 on yield. So this would satisfy the ASME pressure vessel code. This particular vessel was, if it was made out of A36 steel. All right? So anything else you you got questions about related to pressure vessels, we'll tell you tomorrow we're going back to beams again. We're going to combine, first we looked at axial loads, then we looked at bending, and if you remember all these problems when we were bending stuff, we were just bending it, right? No axial loads. Well, what we're going to do tomorrow is start looking at combining those two. This will be in the next section in your book. That's where we're headed tomorrow. As always, if you got questions about something else, you can stick around after I stop recording here in just a second. And I'll be glad to, talk to you, answer your questions. Otherwise, we'll meet again tomorrow. Same time, same back channel.